G'day, it's Mr. Bennett here. Today we're going to be looking at the Young's double slit experiment. This experiment was sort of developed to look at the interference of light waves, and obviously it's a pretty crucial experiment in terms of proving the wave nature of light. So if you think about what we've got a monochromatic light source. So monochromatic means it's only got basically one wavelength. So it's got one wavelength. Alright, so that's the monochromatic light source. When it gets to the slits, what's happening here is it's going to spread out like that. So when it gets to slit number 1 and slit number 2 over here, it's going to be exactly in phase. Alright, so in phase means that it's going to be what we call coherent. That's the term that we use. Alright, so you need to talk about, for an interference pattern to occur, you need to have monochromatic light and you need it to be coherent light. Now, in terms of what's actually happening here, and I'll just draw it, you have to imagine that being a wave going across there, really short wavelength, and there's a wave going a really short wavelength there. Alright, so the idea is that when they go to that third bright band, or fifth bright band, so it's 1, 2, so it's 1, 2, 3, the third bright band, it's going to travel over here with our right angle here, it's going to travel 3 extra wavelengths. Alright, so that's the key thing there. Now, if I was going to do this derivation for this one here, let's change the colour of this. So we've got two triangles. We've got the blue triangle and we've got this triangle here. Alright, so imagine having a triangle going there. We call this distance here 3 lots of the bandwidth, and this one here is the length between the slits and the detection screen. Over here, we go back to looking at our slits. The distance between the two slits there is called our D value. Alright, so that's our D value. So technically what we've got here is two different right angle triangles. We've got our blue one, alright, and so that's going to be the D separation there. And over here, we are going to have, in this case, we're going to have 3 extra wavelengths. And then we've got our red triangle over here, and that's going to be something like 3 extra bandwidths. That's the width of 3 bandwidths. And that is our distance L. So these are both right angle triangles. So if we think about what we've got here, with using this angle here, and for that angle there, that we know that tan theta is equal to the opposite side, 3 extra bandwidths, and over L. And when we go to our blue triangle, we know that that's our angle there, and so therefore we know that opposite and hypotenuse. So sine theta equals 3 wavelengths over D. Now, what we know is, if we think about small theta, and we're talking about a really small angle here, we know that sine theta is approximately equal to tan theta. So what that allows us to do is then to say that 3 wavelengths all over D is equal to 3 bandwidths all over L. And so therefore, if we think about it, we can get rid of the 3 on both sides, and from there we can have the formula, which is the wavelength is equal to the bandwidth, bring the D up to the top line, have the L down there. Alright, so that's one form of the formula that you might use. That will allow us to work out the wavelength of the light source. If we can measure the bandwidth and we can measure the slit separation, and we know the distance from the slits to the screen that we're going to be detecting. We can also rearrange this, and we can say that del Y, the bandwidth, is equal to lambda L all over D. Right, so that's another form of that. In the experiment that we'll be doing, we're going to first of all work out what the D value is. So we're going to do the swapperoo over here. So D is equal to lambda L all over the bandwidth over there. Right, so that's that form. And obviously you can rearrange that for L, and you can say that L is equal to bandwidth times by D all over the wavelength. So technically what we're looking at here is we've got four unknowns. We've got the bandwidth, we've got our L value, we've got our wavelength, and we've got our D value. So when I start thinking about it, we could ask you to find the wavelength, and then we use that form of the equation rearranged. We might ask you to find the bandwidth for a question and use that form. If I want to work out what D is, the slit separation, then that's what I'll use. And if I want to work out what L, the distance to the screen, then I use that form of the equation. So it's a really useful thing in terms of being able to do quite simple questions. Now, the key thing is, if we were looking at any particular question that we get given, we'll be given three of those unknowns. All right, so that's the great thing about that. The derivation itself is really quite simple, and all you need to do for the derivation is really know that triangle. All right, so if you know that triangle, now the derivation might be for the dark band, and the dark band in this particular case is actually in white. So if that's the case, then what we know is that it will be travelling it might travel wavelength over 2, or it might travel 3 wavelengths over 2, or 5 wavelengths over 2. So it'll be a multiple of wavelengths on 2. So it would travel, for the first dark band, half a wavelength extra, then it'll be 1.5 wavelengths extra, and then it'll be 2.5 wavelengths extra, and 3.5 wavelengths extra. So that would be, right, you get the pattern of that. And then when you start looking at the band thing over here, that's only half a bandwidth. That will be 3.5 bandwidths, and that will be 5.5 bandwidths. So again, what you'll find will happen is the number in front will actually cancel out. All right, so that's actually a really useful thing when we start looking at the derivation. Right, this is a key experiment. The experiment that we do is really the same as the theory that we need to know for the exam, which is awesome. All right, so it's the one and the same. Now, let's do a very, very simple question. All right, so a first example might be something like, I've been given a diffraction pattern. All right, so my diffraction pattern, my bandwidth for that between the things might be something like 2 by 10 to the minus 3 meters. Right, and then I've got my slit separation here, which is equal to 2.8 by 10 to the minus 4 meters, and I know this distance to my screen there is in fact 50 centimeters, which is 0.5 of a meter. In that case there, what I'm trying to do is work out my bandwidth. So if I'm trying to work out my bandwidth, then simply using the formula at the top there, over here, so that's going to be my delta y d all over L. So I want to see the substitution into the formula, so that's the key thing I needed to see. So you pretty well get your mark for this bit here. D is 2.8 by 10 to the minus 4, and then that's all over 0.5. Now, what I'm looking for is a value somewhere between 4 by 10 to the minus 7, going through to something like 7.5 by 10 to the minus 7. If this is an experiment that we're conducting, in the laboratory. Obviously you've got eyes, and it's the only way you're going to see the information is by using your eyes. It has to be in that range. Alright, so if you don't sort of get that range, either I've stuffed up with a question, or you've stuffed up. Probably most likely you've stuffed up. Alright, so you get the idea of how you'll list down the information over there. Now I want to talk about the experiment. The experiment has two parts. So the experiment, basically the first part of the experiment, we're going to use a known source of light. So the wavelength is in fact sodium. It's a sodium vapor light, and we know the wavelength. Alright, we will be able to measure L, and we will be able to measure the bandwidth using our micrometer. Alright, so we will know all of those things there. What it's going to allow us for the first part of the experiment is to calculate D. Calculate D. Right, so that's the thing that we're trying to do in the first part of the experiment. Then what we're going to use is we're going to use a whole series of different wavelengths. So we're going to use some colour filters. And since we know D, and since we know L, and since we know our bandwidth, because we're going to measure that each time, then what we can do is we can calculate our unknown wavelength of different light sources. Alright, so that's a really useful part. So essentially what our experiment for the first part with Young's double slit is to find the unknown wavelengths of light based on that information. Alright, so if you refer to the sheet I give you on in terms of having the slit separation, and how you can use the micrometer to measure the bandwidths, that's really important. Alright, so essentially that's what your experiment's about, is first of all doing this. Now if we don't get the right D value, then we're going to have a systematic error. Alright, is that a major problem? It could be. The main thing is though, is when we start looking at the wavelengths and when we start looking at our rainbow colours, Roy G. Biv, right, we know that the red's got a bigger wavelength than the violet, so therefore we're knowing that's going to be something like 7.5 by 10 to the minus 7 on that end, and that's going to go through to something like 4 by 10 to the minus 7 on the other end. So it doesn't really matter what you've got there in terms of, as long as our colour's in the right ratio, then that's going to give you an idea about whether you've done it correctly or not. Alright, so anyway, that's really Young's double slit experiment. Now the last thing I want to just say and show you with this, so we've got our light source from slit number 1, we've got our light source from slit number 2. When we're talking about that travelling further, right, let's say from slit number 1, that's the point. Right, so it's got that particular wavelength. Right, so over here we're talking about it being in phase, so it's got to be in phase. So when we add those constructively together, it's going to be, you know, totally in phase, and you'll get that slight brown. What's actually happening here though, for this thing here, it's actually travelling multiples of an extra wavelength. So in the first case it's travelling one extra wavelength, and then it goes to the next bright band, it's travelling an extra wavelength. Right, so the distance it travels is multiples of a full wavelength for the light bands, and for the dark bands it's travelling multiples of a half a wavelength. Right, so in this case here you're always going to get constructive interference, so your wave pattern over there is going to be a big wave, and when it's out of phase you're going to get annulment. So that's the key essential idea of looking at the interference of waves, and so it does provide evidence that we do have the wave nature of light for this. Alright, so hopefully this makes sense to you, and it's simply, you know, I think it's pretty straightforward, the whole information that we need to do with Young's double slit.